to our module on infectious disease modeling. Over the next bit, we're going to unpack one of the most powerful ideas in epidemic theory, the SEIR model, and the basic reproduction number, R0. By the end, you'll understand how we divide a population into susceptible, infectious, and recovered groups, how a single ratio of two parameters tells us whether an outbreak fizzles or explodes, and how these models guide real control decisions from herd immunity targets to vaccination and culling strategy. This is core ACVPM and board prep material, so let's dive in. Before we touch any equations, let's answer the obvious question. Why bother with mathematical models at all? There are 4 reasons you simply can't ignore. First, experiments are often impossible. You can't deliberately infect 10,000 cattle just to watch an epidemic unfold. But a model lets you run that experiment safely. Second, prediction. Models project the epidemic forward, telling us when cases will peak and when they'll burn out. Third, evaluating control options so we can compare vaccination, culling, and movement bans before committing to costly policy. And fourth, understanding mechanisms because building a model forces you to be explicit about your assumptions. The 2001 UK foot and mouth outbreak proves the point. Modeling shaped an £8 billion decision. Remember, models are tools for structured thinking, not crystal balls. Here's the model itself. We divide the population into 3 compartments: susceptible, not yet infected, but vulnerable; infectious, currently infected and transmitting; and removed, recovered and immune, or dead, and either way, out of the transmission chain. Animals move between these compartments through 2 transitions. Susceptible to infectious happens at a rate of beta times S times I. That's our transmission event. Infectious to removed happens at a rate of gamma times I, recovery or removal. Write those as differential equations, and you've captured the entire epidemic. Just 2 parameters drive everything: beta, the transmission rate, and gamma, the recovery rate. Their ratio, R0, equals beta over gamma, decides whether a disease causes a ripple or a wave. R0 is the single most important number in epidemic theory, so let's define it carefully. It's the average number of secondary infections produced by one infectious individual in a fully susceptible population before any control measures kick in. Crucially, it's a property of the pathogen, host, and environment together, not of the current epidemic state, so it stays fixed under baseline conditions. The threshold rule is what makes it so powerful. If R0 is greater than 1, each case generates more than one new case, and the epidemic grows. If it equals 1, the disease holds steady as endemic. And if it's below 1, the outbreak fades. Biologically, it bundles together contact rate, transmission probability, and infectious period. And the veterinary values are striking. Foot and mouth sits around 4 to 15, BVDV 2 to 5, and Marek's disease above 10. An important distinction that trips a lot of people up: R0 versus RT. R0 is the theoretical baseline, biology only, measured in a fully susceptible population with no immunity and no control. It's fixed for a given setting and lets us compare how transmissible different pathogens are. RT, the effective or real-time reproduction number, is the live signal, the average secondary cases per case right now as the outbreak actually evolves. It accounts for partial immunity, ongoing control measures, and changing contact patterns. The link is simple. RT equals R0 times S of T, the fraction still susceptible. When RT is above 1, the epidemic is growing. Below 1, it's declining. This became globally familiar during COVID-19, but it applies just as well to foot and mouth or avian influenza. Even a disease with R0 of 15 will decline once you drive RT below 1. SIR model actually tell you? Read the output curve, the infectious fraction over time. The SIR dynamics always produce that characteristic bell shape, a slow start, an exponential rise, a peak, and then decline. Here's the key insight about the peak. It happens exactly when the susceptible fraction drops to 1 over R naught, the herd immunity threshold, where the rate of change of infections hits 0. And notice the epidemic doesn't end because everyone got infected. It ends when RT falls below 1 as the susceptible pool depletes. The final size depends on R naught. At R naught of 2, roughly 80% are infected. At 5, it's nearly everyone. Now the good news. Interventions shift this curve. Vaccination lowers S, culling raises gamma, and movement bands lower beta. Combine them and you flatten and delay the peak, easing the strain on your response capacity. Basic SIR model rests on one big assumption, homogeneous mixing, where every infectious animal contacts every susceptible equally. That's rarely true, so we extend the model to add biological reality. SEIR adds an exposed compartment for the latent period when animals are infected but not yet infectious, essential for foot and mouth and bovine TB. SEIRS goes further by letting immunity wane, animals returning from recovered back to susceptible, which enables endemic equilibria and repeated waves. Think BVDV or equine influenza. Age-structured models capture different contact rates and susceptibilities across cohorts. Spatial and network models replace random mixing with realistic farm-to-farm contacts, the state-of-the-art that shaped UK foot and mouth policy. And stochastic models add random variation, which matters enormously in small populations where chance alone decides whether an epidemic even takes off. Each extension fixes a specific place where the simple assumption breaks down. This depends on getting good parameters. So how do we actually estimate beta and R naught from data? There are 5 main approaches. Early in an outbreak, the exponential growth rate method uses how fast cases are rising. R naught is roughly 1 plus R over gamma. After an epidemic ends, the attack rate or final size method back-calculates R naught from the total proportion infected. The seroprevalence method uses post-epidemic serology. R naught is about 1 over 1 minus P. For complex multi-host systems, the next generation matrix gives R naught as the dominant eigenvalue, and the gold standard is fitting the full model with maximum likelihood or Bayesian methods using tools like POMP or RSTAN, computationally intensive, but it gives you beta, gamma, and proper uncertainty bounds all at once. The right method depends on what data you have and where in the outbreak you are. Immunity threshold is where modeling turns directly into a vaccination target. The formula is beautifully simple. HIT equals 1 minus 1 over naught, or over R naught, the proportion of the population that must be immune to stop epidemic growth. But there's a catch. Vaccines aren't perfectly effective, so the coverage you actually need is HIT divided by vaccine efficacy. Take BVDV. With R naught of 4, the threshold is 75%, but at 70% efficacy, you'd need 107% coverage, mathematically impossible through vaccination alone. And foot and mouth with R naught around 15 demands a threshold of about 93%, leaving almost no margin for an imperfect program. That's why high R naught diseases are so hard to control, and why successful programs combine vaccination with biosecurity to lower beta and test and cull to raise gamma. The model is literally driving control program design. all of this play out in a real billion-dollar decision, the 2001 UK foot and mouth outbreak. In February, FMD was confirmed, and within days, 57 premises were infected. Livestock movements had already seeded it across the country before anyone detected it. Early modeling pegged R0 at 4 to 8. In March, Ferguson and colleagues published a farm-level spatial model in Science concluding that ring culling within 24 to 48 hours was needed to push RT below 1. That triggered an intense policy debate, vaccination versus culling, and the government chose culling, holding vaccine in reserve. Cases peaked around 50 infected premises a day. Then RT dropped below 1 in April, with the last case in September. The final toll, 8 billion pounds and 6 million animals. A later analysis showed earlier ring vaccination would have cut losses, reshaping UK and EU contingency planning. The lesson, a transparent quantitative framework beats pure intuition when you must decide in real time. Let's connect each control measure back to the model because every intervention targets a specific SEIR parameter. Vaccination reduces the susceptible pool, S. It's equivalent to starting the epidemic with a lower effective R0. An emergency ring vaccination builds local immunity barriers around new outbreaks. Culling raises the removal rate, gamma, by taking infectious animals out directly through depopulation of infected premises and preemptive ring culling of contiguous farms. Movement restrictions lower the contact rate and therefore beta. And remember the 2001 lesson. The day one movement ban was the single most powerful control act because livestock movements had already seeded the epidemic. The real takeaway is that the most effective control attacks several parameters at once. Combining vaccination, culling, and movement bans is how you drive RT below 1 fast enough to halt a major exotic disease outbreak. And models let us test every combination to find the optimal mix. Sometimes a disease never burns out. It becomes endemic, settling into a long-run equilibrium. For that to happen, you need R0 above 1 and a population above the critical community size, large enough to sustain continuous transmission. At equilibrium, the susceptible fraction stabilizes at 1 over R0, and the system naturally dampens back to these values after any perturbation. The core dynamic is a supply problem. New susceptibles must enter faster than infection removes them, or the pathogen exhausts its host and dies out. Those new susceptibles come from births, from waning immunity, returning recovered animals to susceptible, and from immigration. BVDV is the classic example. Calves are continuously born naive, and persistently infected animals form a permanent infectious reservoir. That's the critical insight. PI animals break the standard SEIR model because they're born infected and stay infectious for life, which is exactly why test and cull of PIs is the cornerstone of every BVDV control program. Actually build these models, here are the practical tools arranged by entry complexity. Start with spreadsheet models, discrete time SEIR or SEIR in Excel or Google Sheets. Perfect for teaching and simple scenario analysis, with no programming required. The standard next step is R packages. EpiEstim for real-time RT estimation, DSolve to solve the SEIR equations in under 20 lines, EpiModel for network models, and POMP for parameter fitting, all free, well-documented, and increasingly the norm in published work. NetLogo offers agent-based modeling with a graphical interface, excellent for visualizing spatial and network spread. And at the regulatory end, purpose-built tools like Interspread Plus and AADIS simulate farm-level foot and mouth and avian influenza outbreaks. These are what USDA, APHIS, DEFRA, and national agencies use for contingency planning. For self-study, Keeling and Rouhani's book has a free companion website with all the model code. Bring it all together with the key takeaways. 1. The SEIR model splits a population into 3 compartments driven by just 2 parameters, beta and gamma, with R naught equal to their ratio. 2. The threshold rule. R naught above 1 and the epidemic grows, below 1 and it fades, and we track RT in real time to see whether control is working. 3. The herd immunity threshold. 1 minus 1 over R naught. Set your vaccination coverage target once you adjust for efficacy. 4. Each intervention targets a specific parameter. Vaccination lowers S, culling raises gamma, movement restrictions lower beta, and the best control combines all 3. And 5. Extensions like SEIR, SEIRS, and spatial models add the biological realism you need for real outbreak response. For your boards, focus on R naught interpretation, HIT calculation, and how interventions act on the parameters. That completes our module. Thanks for watching, and the next module is coming soon. Thanks for joining, and if you found this helpful, please like and subscribe. I'll see you next time.